Okay. So Norden-Heinzen, again, this is a specific bell-shaped curve that is unimodal, so it only has one mode. It is symmetric, and the definition of how it is defined mathematically, we've seen a spreadsheet. And all of these tests that we will do in this class basically assume that the data that we're dealing with is a normal distribution. So all inferential statistics we're doing over the course of the rest of the semester will be assuming this mathematical function, and will assume that this looks exactly like that frequency polygon that I just showed you. So sample size determines how close the distribution of an individual variable really looks like a normal distribution. So the more data points you have, the larger the sample size is, the more closely it looks like a normal curve. So when you only have like a handful of data points, this data will not look in any shape or form like this frequency polygon. So logically, also, if you have bless you. If you have a normal population or a population data set that is truly from a population with a very large sample size, it will be more likely to look like a normal distribution. If you have a smaller sample, it will less likely look like a normal distribution, but the larger the sample grows, the more likely it will look like the distribution, the frequency distribution of the population, and the more likely it will look like a normal distribution. So the example that is given here is, so this is the happiness score, which we can play around with later on. So this is the happiness score of 157 countries that Norden-Heinzen provided. I've downloaded this data from the source. And so you have this data set actually on your canvas, and we'll look at it later if we have time. So basically, if you take a sample of 5, this looks nothing like a normal distribution curve. If you increase the sample size, it starts to kind of more look like a normal distribution. If you have now a sample size of 157, you kind of see at least vaguely that it has one mode, and it kind of distributes more evenly, more symmetrically. This is not strictly true, unfortunately, because it's also the more sample and the higher you come with your sample size, whatever you mean to characterize, the more likely it will look like a really nice, beautiful normal distribution. So, so sample size increases, it looks more like a normal curve. Can you think of variables that might be normally distributed? So typically, most variables that are to some extent interval variables are normally distributed when they have some biologically underlying source. So like blood pressures, cholesterol, all these clinical parameters that we are seeing or that I'm seeing in my world, they are mostly normally distributed. What is not normally distributed, where you have 2 specific states. Like in my case, it's inflammatory parameters. Like somebody is not inflamed, the values are going to be very low. Somebody is inflamed, and these are not really quantitatively changing. You have then a second peak, which is very, very high. Also, things like household income are not normally distributed. Everything that is more population-based is often not normally distributed. So various parameters that have a biological association will be normally distributed. Then the question that Norden-Heinzen want to show you, can nominal categorical variables be normally distributed? And the answer to that is, well, it's not impossible, but it's likely not the case, because you have arbitrary definitions, right? Even if they're ordinal in a way, they're likely not normally distributed, because the definitions are still based rather on a label or on a definition rather than individual actual point, individual data point. So normal distribution you would not find in nominal data. Yes.
The answer is no, you wouldn't find it in nominal. You wouldn't find it in nominal because the differentiations are arbitrary.
Exactly. So if you have, for example, Twitter, percentage of Twitter users in a country, percentage of Twitter users of those that have internet, that was like where we did bar chart and Pareto chart. You couldn't really see a normal distribution because one of the definitions of that normal distribution is that the x-axis actually is defined by numerical values that display the magnitude of the actual variable. And on the y-axis, you have the actual frequency. So that's the definition of a frequency distribution. So now, when dealing with a normal distribution, you're starting off basically understanding as a process that is called standardization. So we talked about this mathematical function that is defined by the mean and the standard deviation and the squared standard deviation, which is the variance. So basically, you can, with standardization, convert individual scores. So if you have a frequency distribution, you have an actual value on the x-axis, and you can convert each individual score into a standardized score that is called the STAT score. And the STAT score is basically the first standardized score that we will be dealing with, because it is in a perfect normal distribution, actually an individual standardized score. So what does that mean? The STAT score, as per definition, is the number of standard deviation a particular value or a particular score is located away from the mean. So that means, in essence, if you have a mean, that is defined as a STAT equals 0. If you have a STAT equals 1, that is one standard deviation above the mean. If you have a STAT equals -1, this is one standard deviation below the mean. And that's how you will carry on characterizing and standardizing your normal distribution curve using this formula. So you calculate an individual score minus your mu, minus the mean, and you divide it by the standard deviation. And that's how you standardize. So when you want to do this now, and let's go now in our country happiness spreadsheet. No, come on. So if we're doing this now in our happiness spreadsheet, happiness score spreadsheet. So we have here data of 157 countries, 157 countries, from Burundi to the US to Denmark. And we want to quantify now a mean. So we know if we calculate a mean, this is basically nothing else but average of B2 to B158. That's our mean. So the mean happiness in all these countries, in all these 157 countries, is 5.382. That's the mean. If I want to know now a standard value, that's actually, it's mean or mu. If I want to know now the standard deviation, the sigma, this would be stdef.p of B2 to B158. So that's the calculation that I don't want you to do for the homework, but it's basically.
Copy and paste stuff.
Oh, yeah, sure. Okay, so these are the two formulae that will allow you to quantify the mean and the standard deviation. So these two essentially allow you now to standardize your normal distribution curve. So if we take this formula here, so we have now a STAT score, and this STAT score essentially is calculated as x, and the x is this. So this is our actual x. This is the x. I'm trying to make this a little bigger. Sorry, it's so small. It's unpleasant to work.
How do you just paste, when you copy and paste it, it doesn't go in? When I copy and paste the image, it doesn't go in. Like,
This formula, you mean? Well, you need to take this from the PowerPoint
Yeah,
presentation.
that's quick.
Did you download it or did you do it from Canvas?
No.
Oh, then it's, so you need to click on it and then you get this field, you need to click it again, that it selects only the text box. It's sometimes a little tricky, but I'm sure you get the hang of it. Okay, so once you have this here, so if I want to calculate now the set score of, let's do Chile. So I go on a C25 and I can label this first. I can calculate now the set score of Chile by calculating. I need to open the bracket. It's the actual X, which is 6.705, minus my mean. And I divide it by the sigma. So now we remember that we always need to lock in the actual reference value. If we wouldn't lock this in, it will basically drag it down. But now we can basically move this formula to whatever country we want to do it if we lock it in. So we do $H $6, $H $7. So this would be now the set score of Chile. And this, in the end of the day, this is nothing else but B25, so the individual score. This is again, it's too small. I'm sorry about that. So B25, that's our X minus our mean divided by the sigma, divided by the standard deviation. And that gets us the individual set. And what does this set actually tell us? It tells us that Chile, assuming a mean of 5.382, that Chile is 1.1 standard deviation located away from our mean. Right. So it's just you're converting it into the number of standard deviation that particular value is located away from that mean. If I do the same exercise now with, let's find a good one. Let's find Laos. And we're calculating now the same formula. So this is, so Laos is B103. All right, let's do this parenthesis. B103 minus $H $6 divided by
Why are you putting the
$H $7, because we want to pull it all the way down later. So locking the cell in will keep the actual the reference cell locked in. So now here we have minus 0.44. That means that the happiness of Laos is 0.44 standard deviations less than our mean. Away from the mean, yes. It's 0.44 standard deviations lower than the mean. That's the standard deviation in a population. That's that was chapter 4, central tendency and variability. We have sigma is the standard deviation for population, and S is the standard deviation for sample, whereas mu is the mean for a population, and M is the mean for a sample. So this being said, now I can basically take this formula and I can just drag it up. And I can drag it up as far as I want. And what you notice here is somewhere around Turkey and Indonesia, there's our mean. You see how it changes here from a negative set score to a positive net score, a set score. And you basically have somewhere in between, you have our mean located. And yeah. So this is basically what you do with standardization. So you standardize it in the number of standard deviations this individual score is located away from the mean. So Nolan and Heinzen show here a little bit of a different example. So they had, I believe the example is the size of students in a class, and they have a mean of 70 inches. Does that make sense? Sounds a little more. But we have a set of equals 0 is 70. You have a set with a standard deviation of 10. You have a set equals 1 with 80, a set of -1 with 60, set of -2 with 50, and a set of +2 of 90. A set of 1.5 would be 85. Simple, right? This is a very simple concept, but it's a very meaningful concept, because essentially you can by that characterize your entire normal distribution according to the mean. As we know, the mean is the individual value and the second individual value, and all the individual values divided by the number of entries. So if you have here a small dog and a large dog, the mean will be in between those two dogs. You have one negative dog and a positive dog. So that's kind of the way you need to look at this, right? So you can, with a set score, right away see whether this is below the population mean or above the population mean. So just the sign will tell you that. So once you have a set score and you only have the set score, you can do exactly the same thing the other way around. Because if you look at the, okay, so let's complete this formula. If we take this formula now and we do this now for each individual entry.
You're supposed to get negative numbers.
Yeah, you have negative numbers, you have positive numbers. Everything below Turkey and Indonesia will be negative because it's smaller than the actual mean. So this is set scores. And yeah, and this is basically giving you now all the set scores for the entire board. So you can pull this formula all the way down and you get each individual set score. So if you want to go now the other way around with this formula to calculate the individual set score, you can now calculate the individual X. So the individual X can now be calculated basically by rearranging the formula, right? So if you multiply now your set with the sigma, you're left with X minus mu. Adding the mu to X multiplied to set multiplied by the sigma gets you a rearranged formula that basically allows you to calculate an individual entry. So if you want to know, so I have the US here was 1.51. I have the individual value. I have an individual set of 1.51, and I want to multiply this with the sigma and add the standard deviation and add the mean. I'm getting to 7.104, which is essentially the happiness score that was reported in average for the US. So you can do the same operation backwards, which is important that you know that. So we will need that with regression analysis.
What was the equation?
Here, X equals set multiplied by the sigma plus the mean. Yeah, it's on slide 13 in the department. So essentially, knowing the mean and the standard deviation allows you to characterize and standardize the normal distribution curve. So once you characterize your entire normal distribution with set score, you have a standardized normal distribution, or a standard normal distribution is basically nothing else but the normal distribution defined by the set scores. And then you can utilize this to build your histograms just based on the set scores. It comes to the same thing. You're just converting it, and it still has the same meaning because mean and standard deviation doesn't change. It's just as a concept important because it allows you. So you can compare apples with oranges, and that's quite powerful because essentially you want to sometimes relate two scores that are numerically not really related to each other, just based on their magnitude in relationship to the population mean. And standardization allows you to do that. And not only is this true for apples and oranges, so not only for the actual fruit department, but also for social research, social science research. If you want to relate variables that are not commonly relatable to each other, that have magnitudes that are inherently different, and you want to compare, okay, so where does this individual locate to the mean of the population based in all his or her emotions, and then relate them also to fear and disgust, which are inherently different matrices, are used and quantified and have a different meaning, but you may, for some research reasons, try to relate them. The STAT score is, the standardization is essentially a way how you can accomplish that. So you standardize them to your population distribution, and you take a population-based distribution to relate two parameters to each other, two variables to each other. Yes, any question?
Yeah, you said that if we take two different, like, broad scores, like broad that
Variables, not scores.
that have nothing to do with each other, and take it to a z-score, then we can compare them. But then why do we have to take the z-score and compare and turn it into a loss? What is that for?
So I didn't really say, if I said, then I misspoke, and not that they don't have to do anything with each other, but they're different in terms of their quantification and in terms of their nature. But there still may be a correlation or some association between, I don't know, I'm just putting this out there. So all emotions will be determined to some extent by the components of all emotions, and that includes fear and disgust. So somebody who is fearful may also be more likely disgusted. I don't know, I'm just making up associations. So there is some inherent association to these two variables, but they're quantified in a different metric, in a different manner, and you want to relate them to each other in their relationship to the population frequency distribution of each of these emotions. So that what helps you. You understand what the entire emotions, what the entire population feels in terms of their emotions, whether they have all emotions, fear or disgust, and you basically relate each individual score to the population frequency distribution. That is what you accomplish, and that makes it easier to compare them across the entire observation period. So emotions have changed over the decades, and you want to see how that is true for all the other variables. And you can, in a time series like here, for example, you can easily see how these have changed based on the population distribution. Make sense?
Yes.
Okay, great. Any other questions? I know as a concept, it's easy to follow, right, conceptually, but the application is a little bit tougher to understand, but you will get there in a second, because now we're getting to an important topic, which is a consequent topic of this standardization. Because not only is the standardization useful to standardize individual scores in relationship to central tendency and variability to the population distribution, but they also allow you, under the knowledge that the normal distribution is basically a mathematical function that creates an area under this function, area under the curve, which in its totality sums up to 100%, you can utilize now STAT scores to quantify the percentile, which is below or above a certain value. So you have that function, and you can basically relate based on the knowledge of this function. You can say, okay, I have a STAT score of XYZ, and a certain fraction of the entire population will be below this threshold. And now we're getting to that. So if we have percentiles to be calculated, we need to recognize a couple of things. And these are just only the major definitions and the major milestones on this normal distribution curve. So basically, when you go from the mean, one standard deviation above the mean, you're capturing 34% of all the data. And the beauty of this is, because you're standardizing it based on a mathematical function, this will always be true. So irrespective of the variable you quantify, irrespective of the nature of this variable, if you have a normal distribution and you have a mean of a certain value and a standard deviation, and you know these two markers, you can always say that between 0 and 1 Z-score, you have 34% of the population. Equally, from 0 to -1, you again have 34. And that gives the definition that you have between +1 and -1 Z-score, 68% of your population captured. And that again is always true. So if you see a scientific article and you see a mean and the standard deviation reported, you calculate Z equals 1 and Z equals -1. You can say 68% of that population, of the sample population that the authors are reporting, is located between that value and that value. If you go a little further and you take +2 and -2, you get an additional 29%, 28%. So this basically gets you to 96%. More specifically, gets you to 95.7. But we rounded here, Northern Einstein rounded. So you have within +2 and -2 standard deviations away from the mean, you're capturing 95.7% of your population. Bless you. If you go for 3 standard deviation, you're capturing an additional 4%. So 95.7 is actually not 4%, it's less. It's actually, you have within +3 and -3, you have 99% of your population. And I really highly flag this because that's the so-called empirical rule. The empirical rule says that within 1 standard deviation, you have 68%, 2 standard deviation, you have 95 or 96%, 3 standard deviation, you have 99%. Also called the rule of I forget the name of this gentleman. So it's the empirical rule and the rule of a mathematician, whose name I have forgotten for now. Okay, please forgive me for that. So we have now the normal distribution standardized, and as per these boundaries, we can define our normal distribution and our population. Any questions? It's logical, right? It's not terribly hard or complicated. It's conceptually, I know it takes a little bit to go along with it, but it will make a lot of sense very soon. Okay, 68%, 95.7, 99%. And yeah, this can be even further refined. And I'm getting to the so-called set distribution table. And I just want to quickly do this exercise. So we have now calculated set scores. We have talked about the empirical rule. And we have talked about the underlying mathematical function. So hypothetically, you can quantify each of these percentages that are below a certain threshold by hand, easily. So if you have a set score, you basically can say, based on this graph here, you can say that everything below a standard deviation of a set score of -2, there 2% of the population is less than -2. If the set distribution table allows you now to characterize negative set scores and positive set scores and the relationship of the normal curve to these set scores in much detail. So essentially, you remember that we had with -1, we had 18% of the data, right? No, 60%. With 34, yeah. So we have 34% of our data from the mean was set equals 0 to -1. So we have at the mean, we have exactly the split into the lower 50% and the upper 50%. And this assumes that the normal distribution is perfectly symmetric and mean, median, and mode is identical. Then we have less than the mean, we have 50%. Higher than the mean, we again have 50%. That's the higher 50%. So if you go now from 0, and so the way you have to read the set score table, you have here the first decimal of the set score. So you have it starting here with -3.4 all the way up to a set score of 0. So if you go from, and you have on the upper hand, you have the second decimal. So if you go here from 0.001 to 0.02, you go all the way to the left. You have an increase for the respective first decimal up until to the next first decimal. So that's how you have to read that. So this column here is 0. This is -0.01. This is -0.02. This is -0.03. So if you go left, that decimal is increasing. The second decimal is increasing. So if you go from 0 to -1, you have here the exact percentage that is smaller than -1. So you have, if you think of the normal distribution curve, everything to the left of -1 comprises 0.1587. So 15.9 or 15.87% of your population is actually presenting with a raw score smaller than that set of -1. So 50 minus 16 is 34. That means you have 34% between 0 and 1. So these are 34%. These 34%, we can look up on the positive side of the set score table. That's the positive set. Here we have from 50 to 84 all values. So this is basically where you go in the upper arm. You go higher than the mean. You go from 0 to +1 of the set score, and you come from a 50 to 84. And that's 34% on both sides of the mean, where the peak of this normal distribution is the highest. So this is where you have the bulk of the data. This is where all your data is. Arithmetically, it has to be there because that's also how you calculate it, right? You calculate the sum of all individual entries and you divide it by the number of entries. So if it has the shape of a normal distribution, that center needs to be in the middle, and around that center, that's where the bulk of the data is, if it's symmetric. So that is the concept of standardization, and this is how you transform your standardized set score, your standardized individual value, into a percentage, into a percentile. And this as a concept is super important. So when you have this, you can do various examples, and you will have a couple of examples like that. So you will, for example, get 2 individual values, and you will need to calculate the set score, the corresponding set score. And you will need to consequently calculate how many % of the population are between that and that value. So just to put this in perspective, so let's say you're being asked, okay, a sample question. Let's say you are being asked to calculate a score of what's a good value? Let's say 7.1, and score 2 is now 6.5. So let's say you want to know how much and what's the percentage of the population that is between a happiness score of 7.1 and 6.5. So now you can easily do that by calculating the corresponding STAT score. So you first calculate the STAT, which is here, individual x, which is this, minus the mean divided by the sigma. That's 1.51. You do the same exercise with this. You say this minus the mean divided by the sigma. Gets you from 1.5 gets you from this one to this one. Okay, so these are the STAT scores, right? And these STAT scores do have corresponding percentiles. So if you go to 1.51, you look this up on the STAT score table, you have plus 1.51. This is so this is 1.5. It's one decimal. This is 0.9345. Oops. 0.9345. Now I have 0.98. 0.98. This is here 0.8365. So now if I have these two percentiles, so these are the percentiles. And now I want to know which fraction of the population is located between these two values. I just have to calculate the difference between those two. So I know I have 93.5% here and I have 83.7% here. So the difference is percentage in range is now this minus this multiplied by 100. So I know now that I have within these two values, I have 9.8% of my population. And that's brilliant, but because by that, you know a lot of information about the population. Yes, please. This is just these two divided. You just built the difference between these two. So these two percentiles are basically read from the distribution table. And knowing these two proportions, actually it's percentiles, it's proportions, right? But multiplying that by 100 just gets you to the percentage, right? And that's how you can basically quantify. And this is the example. These are examples that you will certainly see on the quiz. So I'm just flagging this. So please review how to calculate these things. Okay, any questions? It's not complicated, right? It's like if you go step by step through how it's being done, it's really important that you understand how to standardize the individual score, how to translate this then into actual percentiles and know how to read the distribution table, and then know how to interpret it and bring it to that actual example. It's simple when you essentially have just questions of, so how many percent of your population for blood pressure is between a STAT score of 1.5 and your mean? So that would be simple, because then you just have to calculate the percentile and subtract 50% from it. So that's simple, right? There may be more trickier examples where you have to actually define two different score values, and you actually have to define the percentage of the population in between those two scores. So that's a little bit more of the tricky part. So there are functions in Excel how to do that, but I spare you these for now. I think it's easier if you do it by hand for now to conceptually follow along. But there's a function called norm dist that allows you to do that with an Excel function. But yeah, it's probably easier for now, just like this. Okay, any questions on this? Okay, good. Then we can carry on. So you remember from last time that we did in our R-score example for the village of Ames, we looked into, what is it, sampling? No, that's not good. So we looked into the distribution of the greater living area in Ames. And this basically got us to the point where we saw that if you draw a sample, a random sample, these samples will differ between each other. So if you remember, we looked here into our histogram. So that's the distribution of the greater living area from the first randomly drawn sample. That is the distribution of the second sample. No, this here. This is the second sample. And so we had different samples that were randomly drawn of the size of 60. If we do now an exercise where we calculate a data frame with 500 samples, where we draw 500 different samples, and we're creating this this file, which is here df, which is here the mean of repeatedly drawn samples of the size of 60. So we get 500 different means. We are getting, in the end of the day, a histogram that is, that is essentially looking like this. Not this. Okay. So that looks not really beautiful. I was actually hoping for a better distribution. Not a good example. Okay, that's better. Okay, so it's randomly sampled, right? But essentially what we're looking at here, not displaying it. Okay. So what we're seeing here is the so-called distribution of means. So we're getting individual means of 500 different samples. And these means, this distribution of the means, essentially is normally distributed and is essentially reflecting something different than the sample distribution. And this is important to keep in mind for hypothesis testing. So if you have sample means and you're calculating the distribution, the frequency distribution of a mean, is usually, how should I say, usually the distribution of the sample means distributes normally, even if the source population from which you're drawing it is not normally distributed. So why is this important? Because essentially you want to understand the distribution of a mean that it will likely have if you draw a random sample, assuming that the sample that you're comparing to your population is basically from the same population. So you're kind of testing whether this was really a random sample. So you have a population of the New York City population and you draw a random sample of 100 individuals from this population. You want to compare now, is that mean that I have at my disposition from that sample comparable to the mean of the population in New York City? And so I want to do that essentially by, and I want to replicate this 500 times like I did with Ames. That gives you 500 different means. So basically you want to assume that the variability that you see in the sample and that you know you have in the population makes it likely that you have indeed a random sample where the mean that you have at hand is comparable to the population mean. And thereby you need to relate the individual mean in your sample to that population mean. And you do that under the assumption that if you had drawn 500 different samples, the distribution of these sample means would be normally distributed and would be somewhat related to the variability the data in your actual population will show. Because if you have a lot of variability in your population, the variability in your actual sample means will also be greater. So if you have a parameter and you have, let's say, you have happiness in the New York City population, and you have a lot of variability because there are a lot of happy people and a lot of unhappy people, and you're drawing samples from a population where there's a wide spectrum of different happiness scores, you will more likely have, with your small samples, your 60 or 100 people samples, you will have more variability. So if you draw 500 different samples of a smaller size, there will be more variability. Makes sense, right? If you draw larger samples, then your mean and your estimate of the population mean will be more close to the actual population mean. So the larger your sample, the more accurate your estimate of the population mean. The larger your sample, the more likely you will see less variability in your sample mean distribution. So this relationship between the sample mean and the distribution of potential or assumed sample means from replicated samples that you have drawn, this is basically related to each other based on the central limit theorem. So the central limit theorem basically means to associate the central tendency and the variability of a sample and the variability of the population to each other, and means to establish a relationship between the accuracy of the estimate of the population mean that you have from that sample that you have drawn, randomly drawn, to the population mean. And what's the uncertainty or variability of that sample estimate, that sample mean estimate actually is. So if you have a distribution of means, you basically have less variability as the variability in an actual sample. It will be more likely reflecting the actual population mean, because if you have 500 different means, and all these 500 different means will basically differ from each other, the mean of all these means will basically be a very accurate estimate of the population mean, because in its totality, those 500 means are very likely to reflect that population mean. And that relationship is a little bit hard to grasp, I'm well aware, but it is basically the foundation of hypothesis testing, where we mean to draw a random sample, estimate the variability and uncertainty of that sample based on the variability of the population, and we mean to compare that sample mean to the population mean. So this is the first hypothesis test that we will be discussing on Wednesday. So if you, and here's the graphical example. So we're back to the happiness scores. So these are 150 happiness scores that we have, and we're drawing now a distribution of scores. So that's individual scores. So that's not really a beautiful distribution. And we know that the mean is 5.38, which we see somewhat reflected in this sample. But if we draw now random samples repeatedly, and each of these samples, so these are individual scores. So each of these cells is actually a country. So that's one sample. And now you repeat the exercise by drawing out the same number of samples for a large number of times, and you get an estimate of the mean of that sample. So each of these mean estimates here are actually samples from those 157 countries, and you calculate the mean. This actually will get much slimmer, and the mean of means of all these sample mean estimates will then be a very accurate estimate of the population mean. So this is with replication, you essentially is certain the estimate that you have based on your one sample. So if you replicate that sampling, you will get a more accurate estimate of what the population really looks like. So that's the distribution of the means. And there's a difference. So now we have, we know this would be, if you would want to characterize this distribution, you would do that with a standard deviation. So you would calculate the mean from that sample, you would calculate the individual deviation, you would square this individual deviation, and you would calculate the sum of squares. From the sum of squares, you get the variance, and by employing the square root, you would get to the standard deviation. This variability is to be treated differently because this variability is actually dependent on the variability of the population. Because each individual sample mean has a variability that derives from the actual variability in the population from which you have drawn this sample. So the more variability in your population, the more the variability you actually have in that mean estimate that you have at hand. And therefore, we're introducing now a new measure of variability, which is the so-called standard error of the mean. And the standard error of the mean is basically the standard deviation of the distribution of means. So we have the standard deviation. These are the individual scores. And now we have the standard error of the mean that is basically a measure of the variability of the mean of those samples that you have drawn. And this is now associated to the standard deviation in your population. So you have a certain standard deviation that you know from your population. You divide it by the square root of the sample size of your sample, of that one sample that you have drawn. And you will get an estimate of what arithmetically your standard error of the mean. So this variability of means, this variability will actually be. So this is dependent on the standard deviation from your population. And you can estimate this with the standard error of the mean. And this standard error of the mean is then being used for the quantification of the probability of the sample being comparable or identical to the population it was drawn from. And this is what we will quantify with hypothesis testing. So we're calculating the probability that this sample comes actually from a different population than the population we're comparing it to, whether it's generalizable to the population which we have drawn it from. And you're doing this with a hypothesis test that we will start to deal with on Wednesday. So just again, to show these two different measures of spread. So we have the individual distribution of scores here in red, and we see these are wider. So that's your population. So you have a population spread. Yes. This one? What was the word? Yeah, we're talking about hypothesis testing on Wednesday. No, hypothesis testing. No test. Well, it will test the concepts, but there's no test. Hypothesis testing. So we will test hypothesis. So we're carrying this actually a step further because now we're dealing with a distribution of scores that basically are random samples that have been drawn. And we're getting from the distribution of scores to the distribution of the sample means. And we will compare this distribution of the sample means to the population. Scores versus means, yes, the means are more likely normally distributed. And this will be the formula that we're dealing with. So essentially, we mean to compare our mean, our sample mean, to a population mean. And we're using now the standard error of the mean, and this is sigma m is the sign for the standard error of the mean. We're using this to compare the actual differences between the sample mean and the population mean. And this is to be quantified with the so-called STAT score. And this STAT score is converted into a p-value, into a percentile, which allows us to quantify the probability of this being actually from the same population. And so 1.96 is this 5% p-value that we have discussed another time, and we will talk about this later next time. All right, thank you. Have a good night. Thank you.